So this is a video tutorial to help explain the volume of distribution, and it follows on from what we've been doing last week about, or last lesson about absorption, that when drugs are taken either by the oral route or by the injection route or any other route you can think of, they, first of all, the first protocol is usually with the bloodstream, and they're absorbed into the bloodstream. So we're moving on to the second aspect of pharmacokinetics, which is distribution. And it's basically how the drug distributes around the body. Now, it is quite heavily maths based. It's not really extremely hard maths. And I can hear you all running around screaming with your heads in your hands saying, no maths. But it's really not that bad, I promise you. And hopefully I'm doing this video to allow you to try and either work at your own pace and also recap it and go back and test yourself, etc. So I'm hoping it's going to be an effective way of delivering it. Now, to start with, I'm not really going to bother with a definition. It's on the PowerPoint slides that you can find on Moodle, but really, in layman's terms, what we're talking about with the volume of distribution is when you take a drug, how much of that drug either stays in the blood or goes out into other compartments of the body. We'll talk about that later. So the first basic concept which we all need to talk about really is the fact that drugs sort of dissolve, if you like, in the fluid, and they spread out in the fluid. So the first basic concept is just the sort of basic idea of the mass. So if you had 1,000 milligrams of a drug and you dropped it into 1 liter of water, you can actually work out how much you would expect to find. So, can I get a pen? Yes. So 1,000 milligrams divided by 1,000 milliliters would give us a ratio of 1 to 1. So that would be 1 milligram of drug per milliliter. Okay. We could also write that as 1,000 milligrams per liter. Should I put milligrams there to be technically correct? So if we assume that this one compartment, this one cup of fluid, which contained 1 liter, and we got a tablet and we dropped it in there and it started to diffuse around the fluid, then we could expect to see that there would be 1 milligram of drug per 1 mil of fluid, or 1,000 milligrams per liter. Okay, simple so far. So the average adult male's body, apparently according to this website, contains 42 litres. 40, my pen's gone haywire. 42 litres of fluid. Okay, so if you apply the same sort of maths to it, if we have 1,000 milligrams, which is divided into 42 litres, you get an answer which is milligrams per litre. I'll let you do the maths, but what you can see is that this adult male's body has 42 litres of fluid in it. If you take a drug of 1,000 milligrams and you have 42 litres, if you divide the 1,000 milligrams of drug around the body evenly, you'll get a certain figure of something milligrams per litre. Okay, so that's a bit of the basic concepts stepped up a little bit, but the problem is it's not realistic. It's not realistic because drugs can move from compartment to compartment depending on their lipid solubility. So if we have a blood vessel right here, and we have drug in it. If this drug was like oxygen and like carbon dioxide and the things that we learned about right in the first cell biology unit, it would be lipid soluble, and therefore we'd expect it to go from an area of high concentration to an area of low concentration. We'd expect that drug excuse me, to be able to escape out of the bloodstream easily, and we'd expect it to be able to go easily into surrounding cells and organs. So it would go into the extracellular fluid, the fluid outside the cells. It'd go into the interstitial fluid between cells. It would go into the cells itself because there's no stopping it. It can pass through the phospholipid bilayer. Okay. Some drugs are really good at that. Some drugs will just pass through bilayers as though there's nothing to it. However, some drugs will be potentially larger, potentially more lipid soluble, insoluble, should I say, who can't quite find their way directly through the cell membrane as well. And so this is where we have to come into a little bit more complicated maths. So drugs can move from compartment to compartment depending on their lipid solubility. In other words, how well they can move through cell membranes or plasma membranes, essentially. Upon administering the drug, knowing the plasma concentrations, body weight, and volume of distribution can be used to calculate drug dosage required for a particular patient. And that's where I really want to aim for by the end of this video. So let's move it on. Okay, so we've got a bit of a calculation here, which does a bit more application to the maths that we learned in that last page. We've got the same kind of tablet. We've got 1,000, I should say milligrams, not micrograms, of a drug was administered to a patient weighing 60 kilograms. So this patient is weighed 60 kilograms, and we've administered 1,000 milligrams of drug. You can see that the blood plasma is made of 3 liters of, let's say, water. The rest of the body, therefore, has 39 liters, which makes up the 42 liters on average of an adult male, for example. Now, everybody's different, but we're going to use that as a standard figure. So when we give 1,000 milligrams to this person, 6 milligrams of the drug stays in the plasma, and 994 milligrams of the drug goes into the rest of the body. Now, what a professional would do is they would, after giving a dose of drug, would take a sample of that blood plasma, because we were pretty good at taking blood samples. It's quite accurate. They would take that sample and they would find some kind of figure which would lead them to that 6 milligrams of drug. Okay, so first of all, on our sort of tasks here, what is the concentration of drug found in the blood plasma? Okay, so we use the maths that we learnt about originally, which is, fairly straightforward. We've got 3 liters of fluid and 6 milligrams of drug in that fluid. So if we take 6 milligrams of drug and divide it by the 3 liters, so if we divide it into 3 equal liters, so there's 1 liter, here's 1 liter, here's 1 liter, and we divide that 6 milligrams by 3, you can see that there should be 2 milligrams of drug per liter. So 2 milligrams of drug per liter. So that's the answer to the first question. What is the concentration of drug found in the blood plasma? The answer will be 2 milligrams per liter. And I forgot to say at any point in time in this video, when the question is posed, you can have a go at working out yourself, pause the video and then see what I get the answer to be. And maybe I get it wrong and you can question me and we can work it out together. So here is the key concept that if you're going to understand what volume of distribution is and means, this is the key step that we need to focus on. The question is, if you were to drop the same dose of drug in one container, how much fluid would you need to get the same concentration? So, in layman's terms, we've just dropped 1,000 milligrams into this person, and we've ended up in the blood plasma with a concentration of 2 milligrams per litre. Because a lot of the drug obviously has gone into the body, which we really won't be able to tell as easily as what we can with the blood plasma, because we can just draw it out with a sort of a needle. So here is one container with fluid in. The question is, if you were to drop the same amount of drug, so 1,000 milligrams of drug into an amount of water, how much water would you need to get 2 milligrams per litre? That is the question. So again, if you dropped 1,000 milligrams of drug, the same amount of drug, into a vat of water, a container of water, how much fluid would you need to get the same concentration as over here? Okay, so how do we work that out? Well, if we take 1,000 and divide it by 2, we get 500 litres. So we divided that by that, divided by the drug dose by the concentration required. So 500 litres. So there is a way to check whether that figure is correct. If we had 500 litres in here, how did we work out the same over here? So we had 6 milligrams of drug divided by 3 litres. So we had 6 milligrams of drug divided by 3 litres, which gave us 2 milligrams per litre. So over here, if you've got 1,000 milligrams of drug divided by 500 litres, hopefully you can see that 500 into 1,000 is 2, which gives us 2 milligrams per litre. And that's the maths behind it. But you're probably thinking, so what? So what? Well, this 500 litres is huge. If you imagine a 2 litre bottle of pop times by, can you hear my brain thinking how many times there? That's obviously 250 bottles. So you got 250 bottles. Now, there is only 42 litres of fluid in the human body. So this is what we said at the top, really, when you find your definition of volume of distribution. It is a theoretical value. It means that dropping 1,000 milligrams of this drug into somebody's body and achieving a blood plasma of 2 milligrams per litre is the same as taking one compartment
one compartment, so there's nowhere for the drug to go. And the same amount of drug, the same tablet in one cup containing 500 litres of fluid. And essentially what that means is you've got, out of 1,000 micrograms, you've only got 6 left. It means that a heck of a lot of the drug is able to move from the blood plasma to the rest of the body, because you need such a lot of water, such a lot of fluid to dilute essentially that 1,000 milligrams down to 2 milligrams per litre. So we can say that taking 1,000 micrograms, or milligrams, I should say, of this drug has the same effect of dropping it into 500 litres of fluid. Now, for the fourth task, we can divide this figure by the person's body weight to find out their volume of distribution. So 500 divided by their body weight, which is 60, and I'll let you do the maths. Okay. That is the volume of distribution of this drug. So when you take 1,000 milligrams of a drug, you achieve 2 milligrams of litre, 2 milligrams per litre within the drug plasma. This is the same conceptually as dropping 1,000 milligrams into 500 litres of water, which gives you the same concentration of drug in the fluid. Okay. If it was the other way, if 994 milligrams was in the blood plasma and 6 milligrams of the drug was in the body, hopefully you could work that out and predict the opposite effect that the volume of distribution would have. That would be an interesting calculation. I'll let you do it individually if you like. So what is the real world application? So what does it mean? Well, the dose of gentamicin required to obtain a peak level of 20 milligrams per litre in a 60 kilogram patient, and the volume of distribution for gentamicin is 0.25 litres per kilogram. So the dose of the drug is equal to the volume of distribution times the concentration of drug found in the body, right? So if you've ever seen these in maths, it's called a magic triangle. We can put a times there. We can put two dots, which means something in a second. So we want to find what is the dose of gentamicin required to obtain a peak level of 20 milligrams per litre in a 60 kilogram patient. So a pharmacist or a doctor knows the volume of distribution for a particular drug. It's already been well documented. It's well documented, and you can find that for your drug fairly straightforwardly. So if we know the volume of distribution and we want to work out the dosage, what we have to do is times the volume of distribution by the concentration required in the body. So what we have to do, or what we can do, is 20 milligrams of drug times by 60, which is the weight of the patient, times by 0.25 litres per kilogram, so VD times concentration, should give us the dosage required to achieve that level of drug in the
human body. Obviously, it would change for depending on how heavy somebody is. So I think a quick calculation if I'm not mistaken, should come to 300 milligrams. 20 times 60 times quarter. Okay. Should give you 300 milligrams. 300 milligrams. Now, that is essentially the real world application for volume of distribution. Like I say, a medical professional will know how much the drug distributes from the blood into the different compartments. They know what level of concentration the drug wants to be aiming at, and obviously we can know or have a good guess at about the kilograms of the patient. So we can then calculate the dosage required to achieve that level. And if you think back to your pharmacokinetics graph where drug concentration goes up and then down, and you've got that therapeutic window, that's obviously where we need to be. We know that taking that dose gets 20 milligrams per litre in the body, so we can get that drug into its therapeutic window, and happy days. Maximum benefit with the minimum amount of harm.